Okay, let's talk about the acceleration due to the law of universal gravitation, and we'll also discuss centripetal force when that comes up. So we know that the commonly accepted value of g is 9.8 meters per second squared, but where the heck did that come from? Well, it actually can be derived from this law. G m1, well, that'd be the mass of the object. The other thing in contact when we're talking weight is the mass of the Earth, and this would be the radius of the Earth squared. Now, here's a key thing we understand, that we know Fg, the force of gravity. Well, we've also been using all along mg for that. So it's equal to big G, m1, mass of the Earth, divided by the radius of the Earth squared. M's disappear. So little g is actually the constant g times the mass of the Earth times the radius of the Earth squared. Now, let's put in some numbers and take a look at what happens. The mass of the Earth is a well-known constant, 6 times 10 to the 24th kilograms, and the radius of the Earth is 6.4 times 10 to the 6th meters. Approximately 6,400 kilometers, give or take a little bit. So let's put those in. Big G, or excuse me, little g. Big G is 6.67 times 10 to the negative 11th newtons times meter squared divided by kilogram squared. I'm going to put all the units in and show you what happens with those. The mass of the Earth is going to be excuse me, that's just going to be kilograms because I got rid of a mass up here, so one of my kilograms is gone already. The mass of the Earth is 6 times 10 to the 24th kilograms divided by 6.4 times 10 to the 6th meters, and that quantity squared. Now, if I take a look at this, and you need to try this on your calculator because you need to make sure that you can get this number out of your calculator. When you do all the mathematical numbers, it works out to 9.76. Extremely close. Now, let's take a look at the units and watch what happens to the units. By the way, that should be, hold on just a second maybe. So the meters disappear up here, so the meters are gone. I'm left with newtons per kilogram. This does have to be kilogram squared still. Because what's going to happen now is you're going to have a newton over a kilogram, and remember, newton is kilogram times meters divided by second squared divided by kilograms. I get the units of meters per second squared. So actually, if you put the numbers in, you get 9.76 meters per second squared. Now, why isn't it 9.8? Those numbers were not perfectly right. If you go all the way out to the correct number of sig figs and all that stuff, you'd get the correct answer. So you can actually calculate G. Here's the thing. You can also do some of the same stuff we were doing earlier with force. What's going to happen to G if the Earth all of a sudden, so let's have, what happens to G if Earth, I don't know, squeezes into 1/2 its original radius? Some catastrophic thing happens. What's going to happen to G? Well, G is equal to big G, the mass of the Earth, radius of the Earth squared. Now, we're going to do kind of the same thing we did before. Big G is not going to change, so we're going to leave that alone. The mass of the Earth is not going to change. The difference is this is going to be 1/2 of the radius squared on the bottom. So I get 1 over 1/4, excuse me, can't do simple math today, times big G, mass of the Earth, over radius of the Earth squared. So this reduces down to 4 times G. So therefore, we'd go up by a factor of 4. Now, let's take a look at another neat thing that comes out of this. We know that when objects stay in orbit, and we're going to talk about that more in a future video, we know what happens is as something's moving like this, so let's say something like the space shuttle, we know that it has an FG. We also know that it's moving in a circle, so we know the sum of the forces equal MA, and since it's a circle, We know that it's v squared over r. That's equal to Fg, which is big G m1 m2 over r squared. And watch what happens with this. One of your m's cancels out like that, and what we get here is one of your r's cancels out. That becomes 1r. That r disappears completely. We get v squared is equal to big G, mass of the planet, divided by the radius of the planet. So that will give you the speed at which you need to move. Now we're going to play with this a little bit more later in the future. I just wanted to show you now that I can easily say that in this case the weight actually applies a centripetal force that causes the object to move. So that's kind of a neat thing. We'll play with this a little bit more in the next video. Hope this helped.